To model this simple mechanical system, we have to construct a differential equation. We can do this using second law of Newton, which states that the mass multiplied with the acceleration is equal to the sum of all forces acting on the mass. We have to ask ourselves if a force helps the acceleration or counteracts the acceleration. For instance, if the input level u is increasing, then the spring will move the mass upwards. Therefore, we have a positive force k multiplied with u. The opposite is true for the level y. If it increases, then the spring will counteract that increase, and therefore we will have a negative force k multiplied with y. Then if we consider the damper, we can see that if the speed u is positive, that the damper will move the mass upwards. Therefore, we will see a positive force b multiplied with u dot. Again, the opposite is true for the speed y. If this speed is positive, the damper will counteract that positive speed and will have a pull on the mass. Therefore, we have a negative force b multiplied with u dot. Solving this differential equation by hand can be quite hard, especially if we have complex input profiles on the time signal u. Therefore, it can be interesting to simulate this differential equation, and therefore Simulink is the ideal tool. We can start up Simulink by just typing it in Simulink in the command window and pressing enter. Once we've done that, we can create a new Simulink model by pressing this button. Then we get an empty field in which we can build up the model. First, we will start with the input profile of the road, and therefore we look under the sources, and there we will find the generical input in. And then it's perfectly logical to give this input the name u, which is the position of the road profile. Then we will start with the spring component k multiplied with u. Therefore, we go to the Maths library and look for a gain, which is multiplied with input signal u and gets as a constant k the spring constant. And we can also add that to the name of the gain. To eventually define the acceleration, we have to divide all the forces by the mass m. Therefore, we again use a gain block by copy-pasting it, and instead of k, we fill in 1 over m. Again, we add the correct name to this gain, which is in this case the mass. Now we can say we obtained the acceleration. To go from acceleration to position, we need to integrate twice. Therefore, we look in the sub-library continuous for an integrator, and we add this integrator to our Simulink model. And another one to go from speed to position. In this way, we obtained the output position y. Under the Things library, we can look for a generic output which is given the name y. It can be interesting to label the signals. Therefore, we can easily just double-click on the signal line and then add the name acceleration in this case, or speed, and finally also position, all by double-clicking on the signal lines. At this point, we only used the spring component caused by the input. Of course, we still have to add the forces k multiplied with y, b multiplied with the input speed, and b multiplied with the output speed. To do so, we start from the input signal, and we need the input speed. Therefore, we need the derivative. Again, we go to the continuous library and use the derivative of the input signal to obtain the speed. We have to multiply this speed with the damping constant b. Therefore, we will use this gain and name it the damping. we have to add this damping force to the spring force we already had. Therefore, we go to the mod operations sublibrary and look for a sum, which we can find here. And then we can add these two forces by introducing this sum block. However, if we look at the general equation, we see that the position y itself and the speed y dot also has an influence on the acceleration. It's very convenient that Simulink can use a signal later on in the chain of the model to have an impact on earlier signals in this chain. So to determine the acceleration, we have to know the position. And to know the position, we have to know the acceleration. This sounds very difficult from a mathematical point of view, but Simulink can easily handle such problems. Therefore, we can use once more the sum block, which we copy-paste and introduce in our model chain. Now in this case we don't have to add signals, but we have to subtract signals from each other. Therefore we double click on the block. We replace the last plus with two minus signals. Then we can introduce the effect of the speed of the output. Therefore we copy the damping block. This damping block is not in the right direction, therefore we right click and choose to flip the block. And then we can couple it to the sum block. We use the speed signal for this, and in this way we added the damping effect of the speed. We can do the same for the spring. We again copy paste the block, we right click to flip the block, and we use the position to determine the last remaining force component. Now that the system is complete, we can of course save it. Of course, the system only makes sense to simulate if we couple something to the input and measure the output in some way. For the input, we can just browse the sublibrary sources and look for the appropriate input. But to keep our Simulink models manageable, it can be interesting to pack this whole model into a so-called subsystem. Therefore, we select everything, right-click, and choose to create a subsystem from the selection. The mechanical suspension system is now packed in one block. And now we can indeed add a step to the input signal, a step which is equal to riding into a curb with our mechanical suspension system. Of course, we want to monitor the output signal, therefore under the Sinks library we choose a scope and connect it to this output signal. Of course, this simulation only makes sense if we add the right values to the spring and damping constant. We can, for instance, just take the spring constant 0.5 and fill it in the correct gain blocks. But in that case, we have to be sure that we fill it in at every gain block and do it every time we change something. This is not the proper way of working, and we'll keep the spring constant as a parameter k. We will use parameters in our Simulink model and define these parameters in a Matlab script. Therefore, we start a new script, and in this script we give the value 0.5 to our spring constant, 0.2 to our damping constant, and 0.1 to the mass. And of course we can save this script. It's very important that the script and the Simulink model have a different name. Then we can run this script, and as you can see, the right parameters and the right values are now added to the workspace. Now we can actually run the Simulink simulation by pressing the play button, and when that simulation is done, we will finally get an actual result on the scope window. Now this simulation clearly shows what the position of the car will be if the car with this given suspension system drives into a curb. Now we can use the full potential of these simulations by, for instance, varying a certain parameter, like the spring constant. In this way, we can find the optimal spring constant for a given damping and mass of the suspension system. Now we can easily vary the spring constant according to an array, which we start at 0.1, use steps of 0.1 to go to a spring constant of 1. To run a different simulation for each new spring constant, we use a while loop. To use this while loop, it is interesting to have an index which starts at value 1. We will run this while loop as long as the index is smaller or equal to the total length of the spring array. And then, of course, the actual spring constant is equal to the spring constant corresponding with the actual index. Now we start a Simulink simulation using the command sim, which has an argument that is actually the name of the Simulink model. Once the simulation is done, we increase the index by 1 and then let the loop do its work. This program is okay, but only makes sense if we save the simulation result somewhere. Therefore, we open the Simulink model again and go to the scope. To open the properties of the scope, we click on the gear in the scope window. And then at the History tab, then we can choose to save all the simulation data to the workspace or all the scope data. We give this data a proper name, which is in this case the position y, and this will be saved in an array. To see how this array looks like, we run the simulation, and then we can take a closer look at the output in the workspace by double-clicking on it. We see that the first column corresponds to the time instances of the simulation. The second column corresponds to the actual simulated output data. Now it's interesting to plot this data after each simulation. Therefore, we will use the plot command. We plot y position, and from that array we need all rows and only the first column to have the time data. To have the y data, we need again all rows and the second column to have the actual position values. Of course, if we plot another thing in this figure, we want that the previous plot remains. Therefore, we use the command hold on. It's also important that we have a figure to plot this data in, and therefore, before the loop, we will open a figure box by using the command figure. Now we can run this program, and then we get the plot showing the position of the car caused by riding into a curb and the suspension system given the spring constant K. Of course, we need some kind of legend which tells us which color corresponds to which value of the spring constant K. We can ask for help on the command legend by typing help legend, and then we see that the legend command will need strings as an input. We already have an array which tells us which spring constants are used, but this is a numerical array and not an array of strings. Therefore, we can look into Google for help and ask how to convert numbers to strings in Matlab. And the first result we see already gives us the command. We can just use this num2 str command to convert our k array to an array of strings, and then we can call the legend command with this legend data containing the correct strings. If we run this program, we see that the order of our numbers is not quite correct. All numbers are added to one line. Therefore, we transpose the k-array from a row to a column matrix. And then we see the correct result we wanted, showing for each color which spring constant corresponds to that actual color, and then we can see what happens with the suspension system. As you can see, some lines are smooth, some lines are somewhat less smoother, and the simulation output is not that nice. Luckily, we can determine the time in between two simulation runs ourselves. Therefore, we need to go back to Simulink and click on Simulation Model Configuration Parameters. There in the Solver tab, we can choose for the correct solver. Now it's set up at a variable step solver. It can be interesting to choose for a fixed step solver. In that case, we can specify the time in between two simulations ourselves. For instance, we set it now at 0.01 seconds. So every 10 milliseconds, the Simulink model will be simulated again. If we run this program, then we will see that we obtain much smoother simulation results. Moreover, we see that the simulation runs up to 10 seconds. However, all interesting behavior takes place before 8 seconds. We can also adapt the total simulation time here in Simulink and put it on 8 seconds. It's important to build clear Simulink models that are readable by others and by yourself after some time if you reopen the model. Allowing users to easily follow what is happening in your Simulink diagram, you can use all kinds of tricks like giving certain blocks that do the same a certain color. By right-clicking on it, you can choose Format Background Color and give a certain color to blocks that do the same. This is one way to enhance the readability of your Simulink diagrams. At any place in the Simulink window, you can double-click and then you can add text describing your model, the reasoning you follow to build up the model, etc. One important closing remark concerns the scope. Standard, the Simulink scopes will only capture 5,000 data points. If you have long simulations or detailed simulations with short simulation times, it can be interesting to disable the limitation on the data points to save in the scope. Then we can actually capture all relevant data.